So, we have discussed about the transfer function of the controllers and its time domain input output relationship. Let me repeat that once again. So, P controller, the relation in time domain is Ct is equal to Cs plus Kc into epsilon t. So, this is the bias signal and this Kc is the proportional constant, epsilon is definitely the error, Pi, this Ct is equal to Cs, it contains the integral this proportional controllers part, and additionally there is an integral term, and this tau I is known as the integral time constant or repeat time or reset time. And similarly, this PID, it has Ct equal to Cs plus Kc into epsilon t, Kc by tau I 0 to t epsilon t dt, plus additionally Kc into tau d d epsilon dt. So, this tau d is the derivative time constant. So, you have to note that we can individually tune the weightage of this proportional term, the integral term and the derivative term, because the constants here you see it is Kc, here Kc by tau I and Kc into tau d. So, upon tuning the Kc, tau I and tau d individually, we can actually adjust the weightage of these different terms, and that we will discuss in a topic called tuning of the controller. But before that, let us solve a simple demonstrative example which will give you the idea that how the controller's output changes based on the type of the input. So, it is a demonstrative example. Let us consider it is a PI controller where Kc is equal to 2 and tau I that is equal to 0.5, right. Kc equal to 2 and tau I equal to 0.5, and we have the error signal changing like this. Yeah, 1, this is 0, this is 2, this is 4, 6, 8, etc. and this value is 1, this is minus 1, right. So, we have to draw the controller's output signal. So, you have to calculate it first. So, you see we will be going to plot C prime, right, as Cs is not given, right. So, we have first you see C prime 0 minus just before 0, because actually the signal is something like this, okay. It was 0, then it moves up to 1 at t equal to 0 and then continues with the value of 1 up to t equal to 2 minus, then at 2 it drops to minus 1, drops to 0. So, C prime at 0 minus must be equal to 0. Now, C prime at 0, we have this epsilon equal to 1. So, this part will be contributing. So, it is 2 multiplied by epsilon value, that is 1. So, it is 2, right. Next, C prime, then we will go up to this point, that is 2 minus. So, C prime where the instantaneous value again changes. So, C prime 2 minus will be this Kc, Kc is 2, current value of epsilon is 1, right. Then Kc by tau I 2 divided by 0.5 and the integral, which is the integral or area under this curve, which is 2. So, this 2 integrate the actually 0 to 2 1 dt, because the value of epsilon remained 1. So, it is 2 plus 2 into 2, that 6, and it will grow linearly. Now, C prime at 2, C prime at 2, right. C prime at 2, this instantaneous value is 0. So, it is 2 into 0, but the integral will remain. So, 2 into 2, that is equal to 4. Now, with that it will be continuing up to 4 minus. So, sorry. So, this is 2. Then C prime at 4 minus, it remains same, 2 into 0 plus 2 into 2 equal to 4. Now, C prime at 4, now the value is minus 1 plus 2 into 2, correct? No, this I have done a mistake. This is 4, so this is 10, I think. Yeah, this is 4, this is 8, this will be also 8, right. So, it is at 4, it will be minus 2 plus 8 is equal to 6. Now, C prime at 4 plus, again it will remain at 6. Right, 4 plus means somewhere here. Now, again we have to calculate C prime 6 minus. Now, at 6 minus, you see this is a positive integral, this is negative integral, so it will cancel out. However, the instantaneous value, which is minus 1, will be remaining. So, 2 into minus 1 plus 4 into 2 minus 4 into 2, it is minus 2. Now, C prime at 6, instantaneous value is 0, right, and overall integral is 0, so it is 0, and C prime 6 plus is also 0. So, we have to, the logic is we have to break down the entire domain into different characteristic point, which we have to understand from here, right, from the error curve. So, what will be my profile? Let us say it is 1, 2, 3, 4, 5. Okay, I have to erase this curve. Five, 6, 7, 8, 9, 10, right, 11. So, on this side minus 1, minus 2, minus 3. Let us say here it is 0, then 2, 4, 6, 8. Now, initially it is 0. Okay, let me use this color. Initially it is 0, it will be like this. Next, at t equal to 0, it grows to 2, so it will be like this. Now, because of this integral 2 minus, it will grow to 10. So, 2 minus, it will grow to 10 and the growth will be linear, right. Now, at 2 plus or at 2 it drops to 8. Then up to 4 minus, it will remain at 8. Next again it will drop to 6. Okay. So, it will drop to 6, this is 10, this is 8. Next from 4 minus or 4, it is dropping to 6, then it will continue with the value of 6. 4 plus 6, then right at 6 minus it drops to minus 2, and again because of this integral contribution it will be linear. Then at 6 plus it is 0 and it will continue like this, right. So, this is the profile of the controller, controller's output, that will be the profile. So, it is a kind of demonstrative example by which we have solved the input output graphs of a PI controller. So, similar exercise we can perform for other different types of controller. P controller it is pretty easy, and for D mode, that is a PID controller, we have in PID we have to think about the derivative term and we have to appropriately add the derivative in this appropriate portion of this timeline. So, proportional and integral mode will be augmented by this derivative term in PID controller. So, that is about the controller, and we have already discussed in the previous session its transfer functions. So, next let us move to the final control element, right. We have discussed about this transducer as well. So, let us move to the final control element. You see, the final control element majorly in process industry, it is a pneumatic control valve, right. Now, from the controller in the block diagram, you have seen that if this is the controller, we have simply given the arrow and inscribed FCE in the next block, which is the final control element. Now, if it is a pneumatic controller and controller signal, see the controller signal here, it is 4 to 20 milliampere, whereas the FCE signal should be 3 to 15 PSIG. So, that is why we must have a transducer, this IP transducer in between the controller and the FCE, but generally when we discuss about the block diagram and the transfer function, we do not include this IP. IP will be considered as an integral part of this FCE, right. Now, what is the transfer function of this final control element, considering that final control element is a pneumatic control valve? See, if we think about the final control element, the input is pressure, right. Intermediate output we have discussed in second order system is the stem position, and finally it is the flow rate. So, from this pressure to stem position we have a dynamics involved, and we have discussed about it, that x prime bar divided by p prime bar is equal to this A by Ks, where A is the area of the diaphragm and here it is m by ks s square plus naturally the c by ks into s plus 1. Right. So that is the dynamics, it's a second order dynamics. But generally you see that if m is much less than ks, we can approximate the transfer function as first order. Right. Further, if c is also much less than ks, it becomes a pure gain. Right. So this is second order, this is first order, this is pure gain. So you see the dynamics can be simplified from second order to pure gain based on the relative magnitude of m, c and ks. So next we have to think about the relation between the stem position. So this is pressure, see this is pressure, this is the stem position, which is the intermediate, which we consider as intermediate output, and q the flow rate. Now what is the relation between q and x? Mostly it is a pure gain element, and see when we have discussed in the second order system the structure and the design of a pneumatic control valve, actually the stem position represents the position of the plug and how it is moving into that opening in the valve, which is just like an orifice. So the equation, relation between x and q, that is formalized as q is equal to some constant into fx into under root of delta p divided by rho. So you see that for orifice meter or for restriction flow meters, q is proportional to under root of delta p by rho. So there is a similitude, but this discharge coefficient, then 1 divided by under root of 1 minus beta to the power 4, that is the velocity of approach factor. So these terms we have dropped in control valve and replaced by a constant and a function, right. So this k is called the valve constant, depends on the size of the valve. Right. Whereas fx is normalized, that means either it is 1 or it varies between 0 and 1, and this fx versus x relation known as valve characteristic curve depends on the shape of the plug, right. So more importantly, there are different types of the shape which are standard, right, and accordingly we have different relations, functional relations between fx and x. Like we can have linear valve where the plug looks like this, where fx is simply x, and x also you see it is normalized. What is x? X is not the direct stem position. X here it is normalized stem position. Now in the second order discussion we have given an idea that we mark a point in the stem by means of a pointer and there is a scale, right. and the reading in the scale actually is the same position. Now see, if I write that this is 0 and this is L max and the stem position reads L, then x must be is equal to L by L max. So it varies between 0 and 1, right. So naturally, if fx is equal to x, it will naturally vary between 0 and 1. Now we can have square root. It looks like this. So for the square root, which tentatively looks like this, the relation is fx is equal to under root of x. Right. Fx is equal to under root of x. So here also the lowest and highest value of x considering 0 and 1, we have this fx varying between 0 and 1. So next it is called the equal percentage, right. Here the valve looks like much more sharp kind of profile compared to linear, and here the fx is alpha to the power x minus 1, right. There are alternative relations. We will discuss this equal percentage valve later, right, with detailed understanding and all why it is being referred as equal percentage. So anyway, so when x is equal to 0, x is equal to 0, fx is equal to 1 by alpha, so it is not 0 value, right. It never attains the 0 value, and when x is equal to 1, fx is 1. So that is the equal percentage. We have also hyperbolic shaped this valve plug. It is more flat like this, and the relation is fx is equal to 1 divided by alpha minus 1 into x. Now here also if x is equal to 0, x whenever it is equal to 0, fx is 1 by alpha and x it's equal to 1, then fx is 1, right. So the fx versus x profile, if I draw for individual valves, let us see what are the characteristic curve. So for linear, this is the linear, this is square root, this is equal percentage, this is another equal percentage, right, for different values of alpha. Maybe in the first case alpha equal to 10, here alpha equal to 50, and another we have this quick opening with just like a step function. Here the valve plug looks like this, right. So fx is just like similar to unit step function. That is definitely an idealization. Exactly it is not the step function, but rather it is like this, right. On the other hand, the hyperbolic is something like this for different values of alpha. Maybe for the first case the alpha equal to 10, here alpha equal to 50. So that's fx between 0 and 1, and here it is x between 0 and 1. Now you see this is linear, square root, this is quick opening, these two are equal percentage, and these two are hyperbolic, right? So additionally, you see that we can interpret this fx, the physical meaning of fx, in a different way. So if x is equal to 1, fx is equal to 1, and which will give you the maximum flow rate, right? It will give you the maximum flow rate. You may be thinking that if I count x in this direction, then the plug actually is choking the opening, so definitely the value reduces to 0, right? The flow rate reduces to 0, so how come it is maximum? But if I think that we are measuring this x from this side, right, in the reverse direction, this is 0, this is L max, so there 0 means the valve is fully closed for here to close type of valve, and here whenever it is 1, it is fully open, right? So you think of a reverse directional scale, and we can adjust it from 0 to Q max, which is for the maximum volume flow rate that we obtained from a valve at this maximum stem position. So Q max is K into under root of delta P divided by rho. So what we can write, that Q by Q max is equal to Fx, right? Q by Q max is, we can write that this is equal to Fx, and you see this linear Fx is equal to x, right? So df dx equal to 1, it's an alternative, and fx is equal to under root of x. So here df dx is 1 divided by 2 under root of x, and fx is equal to alpha to the power x minus 1. So df dx is or rather we have to take the log. So log of f is equal to x minus 1 log of alpha. So 1 by f df dx is equal to log of alpha, which is a constant, right? So df dx is a quantity which represents the sensitivity, which is basically a gain, right, a gain equivalent term, and then that determines the gain. So this is called the valve sensitivity, and the valve sensitivity, if it is just equal to 1, it is linear, it's equal to 1 divided by twice of under root of x, its square root, and if 1 by f df dx is constant or df dx is proportional to f, then it is the equal percentage, right? So that much we have to know about the control valve right now. So with that understanding of controller, and you see that this involves no time element. So actually if I write that the transfer function, right, after linearization maybe, Only in case of linear valve we don't have to linearize, but if it is equal percentage, if it is square root, if it is hyperbolic, we have to linearize, and finally we can group everything as KV. So this is a pure gain element, right? So accordingly, a control valve maybe from input considering it is F and output considering it is the flow rate. So it may be a second order system, it may be a first order system, or it may be a pure gain element. Why it is a second order system? Because originally we have modeled this F and X, it follows the second order kinetics, and if it has got the negligible mass of the stem and the plug, it will follow the first order kinetics, right? So it will be overall the first order kinetics because X and Q shares a pure gain relation. And similarly, if the C, another characteristic constant of this valve, which is associated to the friction between the fluid and the stem, that C, if C is negligible relative to the spring constant, it becomes Q and this P and X relation becomes a pure gain element, and as Q and X is also a gain element, so overall it is a pure gain. So with that understanding of controller, final control element, measuring device may be first order, may be second order, it can follow any, or maybe a pure gain as well, right? So next we have to think about the block diagram of feedback control loop. So we are going to discuss the block diagram of feedback control loop, right? We consider a simplest of the system. Now this is an open loop system, right? The system which we want to control, it is an open loop. What is that? We have the system, we are considering only one manipulated variable and one disturbance producing the output. Now what should be the block diagram of this type of time domain schematic? This is an open loop system. Okay. So let's take an example. Constant level, we have discussed it and we have considered this specific system repeatedly again and again. Constant level start tank heater. Right, where T steam has been hypothetically considered as manipulated variable. So what was the dynamic equation? dt prime dt, and that's equal to dt prime dt is equal to this Fi by V Ti minus T, right, plus U At then Tst minus T divided by rho Cp V. V is the volume of the liquid in the tank. So you see this dt prime dt, we consider this as 1 by tau Ki minus T plus K into Tst minus T, right. So we have got the equation as dt prime dt. Probably we have done this exercise, again I am repeating it, 1 by tau plus K whole bracket, or let's have all this in deviation variable form, T prime plus K TST prime. Sorry, this is K into TST prime plus 1 by tau into Ti prime. So, the transfer function of this Laplace transform will give you the T prime equal to 1 by tau S plus alpha into Ti prime plus K divided by S plus alpha TST prime, right. So, individually we have two blocks. So, the block diagram mapping will be something like this. Here we have this manipulated variable. See, here what is the block diagram? TST prime bar is a manipulated variable. It goes to that block K divided by S plus alpha, and here we have another block 1 by tau divided by S plus alpha. The outputs are getting combined, producing the final output Y prime bar, and here we have the disturbance, right. Just from this we have mapped it the block diagram. So, here from we are generalizing it. We have the manipulated variable M prime bar S going to that block which we call GPS, being added from the output of the disturbance block GD, where we have the disturbance signal, and finally producing the output, right. So, this is the process and we refer it as open loop system. So, this is the block diagram of the open loop system. So, the system has been formalized with only one manipulated variable and one disturbance, right. So, with that understanding of this open loop block diagram or the system block diagram, let us pass on to the development and construction of the feedback loops block diagram. So, in the feedback loop, you see the controller is simply single input single output system, right, and its transfer function may be GC, what we have discussed. The final control element, let us write the transfer function symbol as GF, and the measuring device which is this GM, right. So, with that we will construct the block diagram. So, block diagram of the feedback loop. So, in time domain or time schematic or time domain schematic of the same feedback loop, here we have the set point YSP prime t, right, going to the comparator, this is plus, here we have this Ym prime t, right, this is error, it goes to the controller. This is not about block diagram, it is a time domain schematic. Controller generates this controller output C prime t, it goes to that final control element. From the final control element we get the manipulated variable which comes to the process, which also receives the disturbance signal. produces the final output y prime t, and we measure it, the signal in measuring device, and producing signal ym is delivered to this comparator, right. So that's the time domain schematic of the feedback loop. So the block diagram, what will change? This here it is y prime sp prime bar s, which goes to the comparator, right. Here it is y prime bar s producing the error signal epsilon prime bar s, going to the controller block with the transfer function GCS as I mentioned, producing C prime bar s. This goes to GF, that is a final control element block, produces the manipulated variable M prime bar s, and here we will have the process block GPS. There will be an adder, as we have discussed for open loop. This is GDS. Here we have D prime S, which produces the output Y prime bar S. From here we have the measuring device GMS, and it goes to this. So that's the entire block diagram. Now next we have to generate a relation. See, this is closed loop. Previously the other one was open loop, this is closed loop. Right. So for this closed loop system, we have to go for calculating the relation of y prime in relation to d prime and sp, the two inputs ysp and d prime producing the output y prime. So you have to generate the relation in terms of this transfer function of the individual blocks. Now you see epsilon prime bar is basically ysp prime bar minus ym prime bar. Now ysp prime bar minus ym prime is what? Gm into y prime bar. Now C prime bar is this C prime bar is Gc into epsilon prime bar. So it is Gc into ysp prime bar minus Gm into y prime bar, right. Now M prime bar is Gf into C prime bar. So Gf into Gc into ysp prime bar minus Gm into y prime bar, right. Next it is being added and produces again y. So y prime bar is equal to Gp into Gf into Gc ysp prime minus Gm into y prime bar plus Gd into d prime bar. So from here, if we shift this y prime bar to this side, we will get y prime bar is equal to this Gf, or rather this Gc into Gf into Gp divided by 1 plus Gc Gf Gp Gm into ysp prime bar plus Gd divided by 1 plus Gc Gf Gp Gm into d prime bar, right. So this is the overall equation that relates the output to the input in terms of different block diagrams or different blocks transfer function. Now you see that in general, not in process industry, but in general for different types of control with one input and one output, we can go for two different, or we can encounter two different control strategy, right, as the ideal one, or two different control problem rather as the ideal one. So, two different ideal control problems. Right. Now, what are they? They are, you see, they are fast. It's a servo control. Here no disturbance, no change, or rather no change of disturbance, that is d prime t is 0. However, set point changes with time. Right. So, that is rare in chemical process industry. However, in some batch mode of operation we can encounter that. Generally rare in process industry, but sometimes encountered in batch mode. What is that? See, I am processing a ceramic element, processing of, example is ceramic materials, where the reaction or the synthesis in the solid phase of this material requires that the material is to be heated, say it is 30 degree the room temperature, then linearly it should be heated to 500 degree over a duration of maybe 3 hours. Then we should keep it at 500 degree for another 5 hours, and then again linearly we must decrease it to 30 degree, right, over a duration maybe 4 hours. Definitely it is not the actual one, but I am giving a random example, right. Now, in the furnace, it should be a temperature controlled furnace, where the temperature initially must shoot up to 500 degree over a duration of 3 hours. So, there is a specific ramp with which the furnace temperature must change. Okay. So, furnace temperature here is a set point, and which must be actually going through a dynamics, then it should remain constant, and then it should decrease again to 30 degree. So, this is a typical example of servo control. So, though the process, this type of servo control problem is rare in chemical industry, but we encounter it frequently in other automation systems like robotics. See, or maybe we are having a problem where we have to load a truck with the cement bags, okay, or some drums which must be arranged in a specific order. So, you have kept the drums, we have arranged the drums in array in the form of some matrix, right, and from there the same is to be replicated. So, there is a loading pattern, right, and that is facilitated by a robot arm. So, you see, if I think of 2 fingers only in that robot arm, or 3 fingers, so what it is doing? It is moving from certain location to a drum top, picking it up and again loading it at a specific position. So, this robot arms, this tip movement is controlled by something called servo motor, which rotates, which allow a rotation by a specific angle. It does not rotate continuously. Okay. So when it rotates by a specific angle, say here, 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 these are all servo motors because we can actually simulate it by a servo motor. So it's rotating by a specific angle when I'm picking up something. So the robot arm basically facilitates the same action. And it's, if we think the coordinate tip position of this robot arm, it's following a definite locus, and that is the set point. Okay. So that is the set point. Here maybe for the 3-arm tip we have 3 control objectives, and that is to be changing, it's going a transient state, and the desired movement can be described by a continuous and programmable change of these coordinates of the tip position. Because the loading and unloading, what we think in terms of simple action, right, can, if I have to automate it, we have to follow a specific locus and we have to program it in the respective robot arm. So control wise, it is a servo control. Practically there is no disturbance if I have a stabilizer which will give you the fixed electric current supply to this system, and these drums are not changing its position definitely automatically because they are fixed and it's not sliding down. So the location, this target location and the location of the destination, they are all fixed. So under this condition, the robot arm is moving, picking a specific drum and keeping it at a specific position on this truck deck. So that is the typical servo control which is frequently encountered in robotics. Okay? However, rare in chemical industry, but in some batch processing we need to actually face this, or we need to actually implement this servo control. The other one, so if it is servo control, my disturbance is 0. So the respective transfer function, you see, it is y prime bar is equal to Gc Gf Gp divided by 1 plus Gc Gf Gp Gm into Ysp prime bar. Right. So this entire block we can call it as servo block. The other problem is regulatory problem, a regulatory control problem. Common in process industry. What is that? No change of set point. However, nevertheless, the disturbance changes with time. So you see that Ysp prime t is equal to 0. However, this d prime t is not equal to 0. So there this is typically encountered in very common in process industry. So you see that y prime bar is equal to Gd divided by 1 plus Gc Gf Gp Gm into d prime bar. Right. And that block of transfer function is called G regulator. So we can write overall transfer function this y prime is equal to G servo into Ysp prime bar plus G regulatory d prime bar. Right. Now, you see the denominator of both the blocks, it's common, right? And let me explain it again by drawing the block diagram. GC, GF, GP, adder block or adder. Here we have GD, D prime bar producing Y prime bar, and here from we have the measuring block GM going here as minus, here it is plus. Now you see, if I simply open this, right? So now here we have Ym prime, how it is related to YSP? In case of disturbance equal to 0, D prime bar equal to 0. Next, Ym prime will be equal to GC into GF into GP into GM into YSP prime bar. Right. Product of all the transfer functions, whatever of the blocks, whatever are inside the loop, GD is outside. And that specific product term we are having in the denominator of both the servo and regulatory block. So as we have opened the loop, this we often refer as GOL, that is open loop transfer function. Right. So in a sense, this becomes GC into GF into GP divided by 1 plus GOL, and that is also GD divided by 1 plus GOL. Correct? Now you see, what about the numerator? Now in the servo block, we are relating YSP to Y. So if I move from YSP to Y, that is, this is the direction, straight out. So how many blocks we face? Controller block, final control element block, and the process block. We take the product and put it in the numerator. Similarly, when we move from GD to Y, how many blocks we face? Only GD, only one, the disturbance block. We put it in the numerator. So that's the easy way of remembering the entire block diagram's transfer function. That here if I simplify, it is Y prime is equal to GC GF GP into 1 plus GOL into YSP prime plus GD divided by 1 plus GOL D prime bar. So this GC, GF and GP are the product of transfer functions of blocks we face as we move from YSP prime to Y prime, and here this is the same product from D prime to Y prime. So that's the idea of closed loop transfer function. We have discussed the different perspectives and the different control problem. So there are actually three types of control problem. One is servo, another is regulator, another is general, where the set point and the disturbance both changes with time. So that's the general format of feedback control loop problem. So in the next session, we are going to discuss about the dynamics of this feedback control loop, considering a simplified version. Just like we will neglect the dynamics of this measuring device and the final control element, that is GMGF will set equal to 1 for simplification and initial understanding. We'll consider maybe a proportional controller and a first order process. Okay, and with that we will try to understand that if the set point, if it is a servo control, if the set point is being changed by a step input, how the output is going to change if we are controlling a first order process with a proportional controller or a PI controller or a PID controller. Okay. So that's referred as the dynamics of the feedback control loop. We will discuss it in the next session. Thank you.